Welcome to the Deep Dive. Today we're looking into a really interesting challenge in AI text generation, how to make it faster without losing quality.
Right. And we're focusing on something called Latent Refinement Decoding, or LRD. It's a newer approach.
Exactly. A two-stage framework designed for these diffusion-based language models, DLLMs. The promise here is pretty big.
Yeah.
Better accuracy and much faster generation.
Which is needed because the standard way, autoregressive models, they're good, but inherently sequential, token by token.
That's the bottleneck, isn't it? That step-by-step process limits how fast you can go.
It's a fundamental latency constraint. So
Right.
people looked at diffusion-inspired models like LlaDA or Dream because they can generate things more in parallel,
Yeah.
potentially faster.
Potentially, yeah. But they came with their own set of problems, didn't they?
Right.
LRD seems aimed right at those. What were the main headaches?
Two big ones. First, what the researchers call information loss. These models, when they're denoising and aren't sure about a word, they do a hard assignment, meaning they basically give up on their uncertainty. They throw away the probabilities they calculated and just slap a generic ASCII token back in.
So all the thinking it did about possibilities just gets wiped out. Okay. And the second issue?
It's related. Premature commitment. Because it's this hard binary choice, either commit to a specific token or reset to mask. The model can mess up.
How so?
Well, it might commit too early based on just local clues and lock in a mistake that messes everything else up. Or it might be too cautious, constantly resetting to mask, which slows the whole parallel process down.
Right, kind of defeats the purpose. So LRD tries to find a middle ground.
That's the idea, a hybrid approach to get accuracy and speed, and the early results look promising.
They really do. The sources mention accuracy bumps on coding and reasoning tests, plus speedups, up to like 10.6 times faster in some cases. That's significant.
It definitely is.
So let's get into how it works. Phase 1 is called latent refinement via soft diffusion. How does it avoid that hard assignment problem?
Okay, so this is the core shift. Instead of forcing that binary token or mask choice early on, LRD works more subtly in the embedding space. It uses what they call soft diffusion.
Soft diffusion, meaning it doesn't make abrupt changes.
Kind of. It performs these distribution-preserving updates entirely using the vector representations, the embeddings. It creates intermediate states through continuous interpolation, not sudden jumps.
Okay, so it's operating on the meanings or concepts before locking in words. How does it actually create these intermediate states? You mentioned a mix embedding.
Right. So for a position where the model is still uncertain, instead of just putting back the standard mask embedding, it creates a blend.
A blend of what?
Two things. The original ask embedding and a kind of weighted average of the embeddings for the tokens the model thinks are most likely the top-up predictions.
I see. So it's like saying, I'm not sure, but here are my best guesses. Let's keep them in mind for the next round.
Precisely. It lets the model's beliefs gently influence the next step without forcing a hard decision yet.
But isn't there a risk of it, leaning too hard on a wrong guess early on? How is that controlled?
That's where entropy comes in. The strength of that blending, the mixing weight, isn't fixed. It's controlled by how uncertain the model is about that position.
Measured by entropy.
Yes, normalized entropy. If entropy is high, lots of uncertainty, the mix stays very close to the original mask embedding. It keeps exploring.
Okay.
But if entropy is low, the model is pretty confident it blends in more information from that top predicted token. The mixing strength is scaled by a maximum factor, so it never completely replaces the mask, just influences it.
Got it. So it preserves the uncertainty when needed, but incorporates confidence when justified, and the advantage of doing this continuously.
Well, first, you don't lose that distributional information step to step. But crucially, because these updated mixed embeddings are fed back into the model's attention layers.
The different positions can influence each other based on these nuanced beliefs.
Exactly. Self-attention allows for cross-position refinement. The model can build up a more globally consistent understanding before it has to start outputting actual words. It avoids painting itself into a corner with an early, wrong, hard assignment.
That makes sense. It prevents that catastrophic situation where the right answer gets zero probability early on. Okay, so phase 1 builds this coherent but still latent understanding. But we need actual tokens, and we need that speed. How does it transition?
Right. Phase 1 is about getting stable beliefs. Phase 2 is about efficiently turning those beliefs into tokens. The transition trigger is stability itself.
How do you measure the stability of, well, of everything at once? Sounds complex.
They use a clever metric, the KL-divergence between the model's predictive distributions from one step to the next.
Okay, so it measures how much the model's overall opinion changed.
Essentially, yes.
Right.
When that KL-divergence drops below a certain threshold, let's call it tower fine, the model figures, okay, my beliefs have settled down enough, and it switches to phase 2.
And phase 2 is adaptive sampling and predictive feedback. What happens here? Tokens start appearing.
Yes. Now the model starts making hard assignments, but strategically. It looks for the positions where it's most confident, the lowest entropy ones, and converts those into discrete tokens.
Progressively.
Progressively. But here's another key LRD refinement. For the positions it doesn't finalize in a given step.
The ones it's still unsure about.
Right. Instead of resetting those back to a plain mask like older methods.
Let me guess, it uses the converged soft embedding from phase 1.
You got it. It uses that richer, nuanced embedding that phase 1 works so hard to stabilize.
So even the uncertain parts retain context. They don't start from scratch each time in phase 2. That sounds like it would speed things up.
It's a crucial part of the predictive feedback loop. That richer context helps the remaining positions converge faster. And this whole phase 2 process has another trick for speed: adaptive early stopping.
Okay, tell me about that. Is that different from the transition trigger?
Similar idea, different threshold. It keeps monitoring that KL divergence, the stability score. If the score drops below a second, even lower threshold, tau decode.
It just stops, even if it hasn't reached some fixed maximum number of steps.
Correct. It stops automatically. This means simple prompts finish quickly, complex ones run longer. The model adapts the generation length based on the task's difficulty, not a fixed iteration count.
That sounds much more efficient than just running, say, 10 steps regardless.
It is. And the performance results bear this out. They tested LRD on models like LlaDA 8B and Dream 7B.
On what kinds of tasks?
Coding benchmarks, HumanEval, MBPP, and also reasoning tasks like GSM-8K and MatchA500. Pretty standard tests.
And the results. Accuracy first.
Accuracy improved consistently. On HumanEval, for instance, they saw gains up to 6.3 percentage points with one of the Dream models. Even on the tough MatchA500 reasoning test, it added 3.8 points.
So it's not just faster, it's actually producing better answers.
Seems so. And the speedups were, well, sometimes dramatic.
You mentioned 10.6x earlier. Where did that happen?
That was the peak, yeah. On the MBPP coding benchmark, using the Dream instruction-tuned model generating longer sequences, 124 tokens, but even in the worst case, it was still 1.2 times faster.
A minimum 20% speed up, potentially over 10 times faster. That's impressive. Where does that speed come from mainly? The mixing or the stopping?
The paper suggests it's both working together. The mix operation helps beliefs converge faster initially, and the adaptive stopping cuts off the process as soon as it's stable, avoiding wasted computation.
They also looked at how quickly things stabilized in phase 1, right?
They did. Convergence analysis showed that, for example, on HumanEval, nearly 70% of the samples had stable beliefs by just the second step of phase 1.
Wow, so that initial refinement is really quick for most cases.
It validates that phase 1 doesn't need to be excessively long to do its job.
Okay, to really understand what makes LRD tick, we need to look at the ablation study. They took hearts away to see what broke.
Standard procedure, yes.
Yeah.
They isolated the effects of the mixed embeddings and the early stopping.
And what did they find? Which part matters more for what?
It was quite a clear split. When they removed the mixed embeddings, the whole soft blending and feedback part accuracy took the biggest hit, sometimes dropping almost 3 points on HumanEval.
So the mixing is key for quality.
Seems to be. But when they removed the adaptive early stopping,
Let me guess, speed plummeted.
dramatically, it didn't just go back to the baseline speed. Sometimes it was even slower because the model was doing the refinement work without the efficiency benefit of stopping early.
So early stopping is the main driver for the speed up. Interesting trade-off. The refinement adds a little overhead, but the stopping mechanism pays it back with interest, and you get better quality from the mixing.
That appears to be the dynamic. They also tweaked the parameters within LRD, like that mixing strength, the true value.
Right. How much of the top prediction gets blended in?
They found extremes were bad. Zero mixing is just the slow baseline. But full mixing was too aggressive, it destabilized things and hurt quality.
So the sweet spot is somewhere in the middle. A bit of mixing.
Exactly. Constrained exploration. Enough blending to guide the model, but keeping it close enough to the mask embedding to stay stable.
Did they look at how many tokens needed to be in that top P mix?
They did, and interestingly, you don't need a huge number. accuracy seemed to level off pretty quickly, even when mixing only included a small fraction of the vocabulary, like maybe top 10% or 20%. P was zero point 0.2.
So it's more about enabling the mixing mechanism than about the exact number of candidates included.
That seems to be the takeaway. Just allowing that token information to flow back into the latent space makes the difference.
Okay, so wrapping this up, LRD looks like a really smart, unified way to tackle the problems of diffusion models. Phase 1 uses that soft, continuous refinement to build coherence without losing info.
And then phase 2 uses the stability measure, the KL-divergence, to transition and then stop efficiently, using feedback from phase 1 to maintain quality.
It really is about finding that balance, isn't it? As the ablation showed, you need that mixing in the embedding space for accuracy.
But too much mixing breaks it. The key seems to be this idea of constrained exploration, just enough information from the likely tokens to speed things up and refine without throwing the whole system off balance.